If you could teleport Stephenson 218 to the exact position where our Sun now stands, the surface of that star would extend beyond the orbit of Saturn. Not close to Saturn. Not somewhere in the middle ground between Jupiter and Saturn. It would engulf Saturn entirely, its blazing surface stretching past the planet's rings and pushing even further into the outer reaches of space. Mercury, Venus, Earth, Mars, Jupiter, and everything within the Saturnian system would be submerged inside the body of a single star, drowned in plasma at temperatures of thousands of degrees. In an environment where the distinction between planets, orbits, and moons would simply cease to exist. No system would remain. Only the hot, turbulent, incandescent interior of an object that would make our Sun look like a forgotten speck on a scale it could barely begin to represent. This object is no hypothesis, no work of science fiction. Stephenson 218 is real. It lies approximately 19,000 light-years from Earth in the direction of the constellation Scutum, partially hidden by the dense dust clouds that dominate the most compact regions of the Milky Way's galactic plane. Its radius is estimated at around 2,150 times the radius of the Sun. To transform that number into something the human nervous system might actually feel, if you were to travel across the surface of the Sun at the cruising speed of a modern commercial aircraft, around 900 kilometers per hour, completing a single lap around it would take just over 6 months of continuous, uninterrupted flight. To complete that same journey across the surface of Stephenson 218 at the same speed, you would need more than 1,300 years. You would take off before the European Middle Ages, pass through centuries of human history, wars, revolutions, scientific discoveries, generations born and grown old, and land in a future no living human being can imagine. And at the end of that journey, you would simply be back at the exact point where you started, having gone nowhere beyond the surface of a single star. There is a specific difficulty the human brain faces when confronted with magnitudes of this order. The number 2,150 solar radii written out in a sentence or spoken aloud produces no emotional response proportional to what it actually describes. Our cognition was built over millions of years of evolutionary pressure at a completely different scale. Meters, kilometers, perhaps a few dozen kilometers were the proportions that mattered for survival. And it was at that scale that our intuitive sense of magnitude was permanently calibrated. The cosmos gave no consideration to that when assembling its own proportions. That is why physical comparison works better than a raw number. The Voyager 1 probe, launched in 1977, traveled at tens of kilometers per second and took 3.5 years to reach the orbit of Saturn. That entire distance from Earth, past Mars, past Jupiter, out beyond the rings of that ringed world, would fit entirely within the radius of Stephenson 218. Our Sun would vanish inside it like a grain of sand lost at the bottom of an Olympic swimming pool, invisible without instruments, irrelevant at any comparative scale. The story behind that number is itself revealing about how science works. For decades, the title of largest known star shifted between different candidates. Why Canis Majoris dominated astronomical conversation for a long time, with radius estimates that shifted as measurement techniques improved. Then Westerlund 126 entered the debate with an estimated radius of around 1,700 solar radii. Then other candidates emerged as the precision of instruments continued to advance. Stephenson 218 was catalogued as a member of a star cluster in 1990, but its true dimensions took years to estimate with the precision needed to reveal its actual magnitude. The fundamental parameters for calculating a star's radius are its surface temperature and its luminosity, and measuring both with precision in distant stars, partially veiled by interstellar dust, demands techniques that are still being refined. Each improvement in that measuring capability brought Stephenson 218 into a firmer position among the largest stellar objects science has ever documented. This recurring pattern, the universe consistently revealing itself to be larger than any previous measurement had recorded, is no historical accident. It is a direct consequence of observing an immense cosmos from a single fixed point, with instruments that improve gradually across generations of astronomers and engineers. Each cycle of technological refinement allows us to reach deeper into space, to resolve objects that once blurred together into indistinct smears of light, and to measure with precision details that once remained crude estimates. In the case of the most massive and most distant stars, the result has been consistent across decades. The boundary of what we know to be possible in terms of stellar size keeps pushing beyond what had previously been established. Stephenson 218 is the current limit, star, not the limit of what exists. What it forces us to recognize goes beyond scale itself. It demands a profound revision of the way we think about the sun, that star which warms our skin every morning, which sustains every act of photosynthesis on this planet, which drives the winds and keeps the oceans liquid, which made possible the existence of all complex life on Earth. It is a completely ordinary star. There are hundreds of billions of stars comparable in size to the Sun within the Milky Way alone. There is nothing exceptional about the Sun in terms of volume or mass within the galactic context. What makes it absolutely extraordinary to us is exclusively its position, close enough to sustain life, stable enough for that life to evolve and diversify across billions of years without interruption. In sheer size, in terms of cosmic proportion, the Sun would vanish beside it. Stephenson 218. But Stephenson 218 has no habitable planets. The Sun has Earth. Sometimes the right star is not the largest one. It is the one in the right place. A star does not simply grow by accumulating more material. What defines the final size of a star is a permanent battle between two forces, forces that push against each other with equal fury, determining moment by moment whether the star expands, contracts, or holds in balance. On one side, gravity pulls all the gas, composing the star inward, violently, crushing the core with ever-growing intensity, heating the plasma to temperatures that ignite nuclear reactions, relentlessly trying to collapse the entire object into itself. On the other side, radiation pressure, the energy unleashed by nuclear reactions deep in the core, pushes outward in every direction, holding the outer layers up against the pull of gravitational collapse. A star exists for as long as these two forces cancel each other out, maintaining just enough equilibrium. And the size it reaches is determined by the intensity with which that balance is established. For a star like the Sun, that equilibrium is relatively stable for reasons rooted in its initial mass. The Sun holds enough hydrogen to sustain nuclear fusion in its core for a total of 10 billion years, burning at a rate that its own gravity demands. Now imagine what happens when the initial mass is tens of times greater. With more mass compressing the core, the temperatures deep inside climb far higher, and fusion blazes at a far greater rate. And the resulting luminosity, the sheer volume of energy released every second, scales with extraordinary speed. Stars of extreme mass can shine hundreds of thousands of times brighter than the Sun. And that enormous energy generates a radiation pressure that literally drives the outer layers outward with ever-increasing force, inflating the star to proportions that have no parallel among lower-mass stars. But physics imposes a hard limit on this process, known as the Eddington limit, a boundary that defines the maximum luminosity a star can sustain before radiation pressure completely overwhelms gravity and begins expelling matter into space at an accelerating rate. Extremely massive stars that approach or exceed this limit begin shedding material through stellar winds, torrents of plasma ejected from the surface at thousands of kilometers per second. This means the largest stars in the universe by volume are not necessarily the most massive in terms of how much material they still contain. In many cases, they are stars that began with colossal masses, and that, over the course of their evolution, shed a significant portion of that mass into space, while their outer layers expanded relentlessly as they aged. Stephenson 218 is classified as a red hypergiant, the most extreme class of evolved star that astronomy has ever encountered. Stars that reach this stage have passed through the red giant phase, as the Sun will in roughly 5 billion years, but they have swelled to dimensions far beyond anything a solar mass star could ever achieve. The surface temperature of a red hypergiant is relatively low for a star, hovering around 3,000 to 4,000 Kelvin, compared to the Sun's roughly 5,700 Kelvin, which gives them an intense reddish hue when observed through the right instruments. But that moderate surface temperature, combined with a radius of staggering scale, yields a total luminosity that can exceed 300,000 times that of the Sun. This is no dramatic exaggeration. It is simply the result of multiplying a reasonable temperature by a surface area that defies every human intuition about what a star can be. To grasp what that luminosity truly means in terms of raw energy, consider this: the Sun alone supplies all the energy that warms the oceans, drives Earth's atmosphere, sustains the photosynthesis of every plant on the planet, and illuminates the entire solar system. Now multiply that energy by 300,000. That is the volume of energy escaping from the surface of Stephenson 218 every single second. If you could place it at the same distance the Sun stands from Earth, it would not simply appear as a brighter point of light in the sky. It would be an overpowering presence, one that would completely shatter the energy balance of the planet, rendering every atmospheric, oceanic, and biological process utterly unrecognizable. In the face of such overwhelming radiation, the internal structure of these hypergiants is equally counterintuitive. When we picture the interior of a star, we tend to imagine something dense, compact, pressurized. And at the core of any star, that is exactly what you find. But in the outer layers of an object like Stephenson 218, the plasma is so expanded and so diffuse that its density falls below that of the very air you are breathing right now. The outer layers of this star are technically a hot vacuum, incandescent, luminous, yet carrying almost no matter at all. What makes the star so enormous is not that it is compact or dense all the way to the surface, but that its outermost layers have spread across a sphere of such staggering proportions that it swallows distances the human mind associates with entire planetary systems. Most of the volume of Stephenson 218 is glowing emptiness, thin plasma, drifting through a space no planet has ever filled, sustained by the pressure of radiation rising from the core and pushing everything outward. The convective cells that carry energy from the core to the surface. In these hypergiants are structures whose sheer size dwarfs entire smaller stars. In our own Sun, convective cells, known as granules, measure roughly 1,000 kilometers across and last only a few hours before dissolving and being replaced. In hypergiants, that phenomenon explodes in scale. Individual currents of hot plasma, rising, expanding, cooling, and sinking, can reach dimensions comparable to the radius of the Sun itself, Saturns, or larger, creating a surface dynamic that is fundamentally unlike anything our Sun has ever produced. Whirlpools the size of entire stars, churning inside an object that consumes whole planetary systems. The most immediate sign that a red hypergiant is something unlike any other star is its variability. Stars like Stephenson 218 do not shine with a steady light. They pulse, oscillate, expand, and contract in cycles that manifest as measurable variations in brightness across weeks, months, and years. When astronomers monitor this kind of object over time, they record fluctuations that reflect the internal processes of massive convection, variations in the stellar wind, and adjustments in the outer layers responding to shifts in pressure and temperature from below. Each pulse of this star involves such absolute quantities of energy that the variations of our own sun seem imperceptible by comparison. A fluctuation of just a few percent in the luminosity of Stephenson 218 represents, in raw energy, a considerable multiple of the sun's entire energy output over the same period. The stellar wind of a red hypergiant is yet another demonstration that we are witnessing physics operating in an extreme regime. The sun continuously emits a solar wind. Charged particles streaming into space at hundreds of kilometers per second create the polar auroras, shape the heliosphere, and over the sun's total billions of years of life will amount to a mass loss totaling roughly 0.1% of its original mass. For hypergiants, the numbers are radically different. They can eject the equivalent of the sun's entire mass every few thousand years through their stellar winds and mass ejection episodes. On an astronomical scale, that is an extraordinarily rapid rate of dissipation. The star is actively unraveling itself, creating circumstellar nebulae, shells of gas and dust surrounding it, which can envelop it so completely that part of its light is reabsorbed and re-emitted at infrared wavelengths, making objects like Stephenson 218 brighter in infrared than in visible light. This continuous mass loss transforms hypergiants into objects with extraordinarily short lives in cosmic terms, not merely because they burn through their fuel at a far greater rate than smaller stars, but because they are actively dissolving. A star with the mass required to reach the red hypergiant stage lives for only a few million years in total, compared to the sun's 10 billion. To put that in perspective, if the history of the solar system were condensed into a single 24-hour day, the sun would be at the midpoint right now. 12 hours elapsed, 12 remaining. A hypergiant would live for little more than 20 minutes on that same scale. It emerges, blazes with incomprehensible intensity, and reaches the end of its journey before the cosmos around it has had time to notice it was ever there. What makes this life cycle so fascinating is not the brevity itself, but what happens during it and after. Throughout its existence, a red hypergiant functions as a factory of elements. In its core, successive nuclear reactions transform hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, silicon into iron, producing concentric layers of progressively heavier elements in a process that deepens as the star grows older. Every element produced represents energy released and matter transformed. The heavy elements that exist in the universe, carbon, oxygen, nitrogen, phosphorus, silicon, iron, and dozens of others, were forged in the hearts of stars like these, and would not exist in any appreciable quantity across the cosmos, were it not for objects massive enough to reach the temperatures and pressures required to synthesize them. This synthesis of elements is one of the reasons why objects like Stephenson 218 are far more than astronomical curiosities defined by their sheer size. They are active agents in the chemical enrichment of the galaxy. Every stellar wind that expels processed matter into the space surrounding the star. Every episode of mass ejection that sculpts circumstellar nebulae. Every particle of dust that condenses within those nebulae. All of it is returning to the interstellar medium material that has been transformed by the nuclear process. That material mingles with the gas of neighboring molecular clouds. Eventually, it collapses to form new stars, and around those stars, planets, composed of elements that would not exist without the earlier generations of hypergiants that forged and scattered them. It is a cycle of cosmic recycling that never ceases, one in which every colossal dying star is in truth sowing the conditions for everything that follows. The inevitable question that rises from this understanding is what becomes of all that volume, all that processed matter, when the hypergiant finally reaches its end, when the nuclear fuel is exhausted, when the concentric layers of progressively heavier elements arrive at iron, and fusion no longer releases enough energy to hold the star against the crushing pull of its own gravity. What is the fate of an object that, at its peak, swallowed entire solar systems whole, without effort? No star endures forever. This is one of the first things modern astronomy established with clarity, and at the same time, one whose implications are least fully grasped by human intuition. When most people imagine the death of a star, they picture something that simply dims, that slowly fades until it goes dark, like a flame consuming its last fuel. But the end of a hypergiant like Stephenson 218 bears no resemblance to that. It is a violent transformation in terms of the sheer energy unleashed, but completely ordered in terms of physics, and what it leaves behind is, in most of the ways that matter, more significant than everything it was throughout its entire existence. When the nuclear fuel of a massively stars is exhausted, the process that determines the end is precise and inevitable. Iron accumulates in the core, the element at which nuclear fusion no longer releases net energy but absorbs it. At that point, the radiation pressure that sustained the star against its own weight for millions of years collapses in fractions of a second. The core implodes under gravity in an interval of time that human perception cannot register, not in minutes, not in full seconds, but in milliseconds. The outer layers of the star, which in an object like Stephenson 218 stretched across billions of kilometers of diluted plasma, are swept outward by a shock wave propagating at speeds equivalent to an appreciable fraction of the speed of light. The result is a supernova, an explosion that for days or weeks can outshine entire galaxies with their hundreds of billions of stars visible across distances that defy human scale. What is hurled into space in that explosion is an extraordinary mixture of everything the star forged throughout its lifetime. Carbon, oxygen, nitrogen, silicon, sulfur, calcium, iron, and dozens of other elements are expelled at tremendous velocities into the surrounding interstellar medium. That material does not vanish. It mingles with the gas of neighboring molecular clouds, enriching them with the chemical complexity that only nuclear fusion inside massive stars can create. Eventually, these enriched clouds collapse under their own gravity to form new stars. Around those new stars, heavier material condenses into rocky planets. And on rocky planets with the right conditions, the chemical complexity built by generations of dead stars can eventually give rise to biological structures, molecules, cells, organisms, and perhaps something capable of looking up at the sky and asking where we came from. That question has an answer that astronomy can offer with extraordinary precision. The carbon atoms in your body's cells were forged inside stars that died before our sun ever existed. The iron coursing through your blood, carrying oxygen to every tissue and organ, was synthesized in the cores of massive stars that exploded and scattered their contents across interstellar space before the solar system even formed. More than 4.5 billion years ago, the oxygen you are breathing right now, as you hear these words, was produced by nuclear fusion inside stars that no longer exist. You are in a completely literal and verifiable sense, stellar matter, not metaphorically, not poetically, but chemically and physically, were traceable to objects that were probably not very different from Stephenson 2.18. This connection is rarely felt with the intensity it deserves, because we tend to perceive the cosmos as something distant, an external backdrop to life, a decoration in the night sky, separated from everyday experience by an insurmountable boundary. But the elements that make up every cell of your body did not come from Earth. They arrived on Earth as part of the material that formed the solar system, and that material arrived in the solar system as a direct inheritance from stars that lived, burned, and died before our sun ever existed. The largest star, catalogued by science, more than 19,000 light-years away, lies on the far side of the galaxy, yet the process that governs it, nuclear fusion, elemental synthesis, the redistribution of processed matter, is the very same process that produced every atom allowing you to exist right now. The distance is real. The separation is an illusion. When you look at the sun now, after everything described here, it is a different object, not smaller in the sense of diminished, but contextualized in a way that was not possible before. You know it is an ordinary star in a universe that contains hypergiants capable of swallowing your entire solar system without even noticing. You know it stands at the midpoint of its life. And that, when it finally expands into a red giant and then releases its outer layers into a planetary nebula, the material that constitutes it will also be scattered across space. The sun, too, will make its contribution. The cycle does not end with the hypergiants. It encompasses every star, of every mass, in every galaxy, in an unbroken chain of transformation that has persisted since the earliest moments of the universe and shows no sign of ending. Stephenson 2.18 is simply the extreme case, the most dramatic example of a process that has been responsible for building literally everything you can see, touch, and be. A question I want to leave with you to consider, knowing that some of the atoms composing your body once passed through the interior of stars that existed and died billions of years before the sun ever formed. Does that change something in the way you think about yourself in relation to the universe? Leave your answer in the comments. It is one of the questions that arises naturally when astronomy ceases to be a distant spectacle and begins to be a story that includes you directly. If the scale and nature of the cosmos is the kind of subject that sets your mind working in dimensions that no other topic can reach, subscribe to the channel so you don't miss what comes next. The universe has far more to reveal than any list of numbers can ever capture. And if someone in your life still doesn't know that the largest star catalogued by science could swallow Saturn with room to spare, that is exactly the person you should share this video with right now.